Just so everybody understands, our goal is to be able to determine how many times this thing will oscillate in a month at this length. I said a minute before. Well, we'll do a month. Okay? But if we can figure out a minute, we can multiply by the number of minutes in a month, right? At some period, okay? So we need to know how frequently this thing is oscillating or how long it takes to complete one oscillation, okay? Now, a cycle is from here, over, and back. That's 1, 2, 3. We understand what a cycle is, right? Now, in MCR, we counted half cycles. So we counted 1, 2, 3, 4, 5, but we didn't count it for that length. We counted it for, about this length, and this length, and this length. And we can see that the shorter it gets, the faster, or the more frequently it oscillates. So we got data. And we have that on camera. So you can see the entire process, and you can corroborate the data if you so wish. I'll give you a suggested exercise. It wouldn't take too long. Where you just, do 5 30-second counts. You would get data that you could then translate into a more accurate graph than we've got here. Okay? So at least think about what you would do if you were going to do that exercise, which most of you probably, because it's finals time and you don't have time to do it, won't. Okay?
You're very correct.
I'm sorry?
You're right.
Yeah, I know. There are people who would. And hopefully, if it's beneficial to you, you can, because it'll help you understand the interpretations, right? Because we're going to do a full interpretation of this function, and we're going to do the simultaneous equations that give us the function. We're going to go through the whole process that covers a good percentage of what you need to know in the course, okay? And gives you a perspective, an idea. Things just aren't working right. It's been a long semester. One of them ideas. If I let that pronunciation evolve a little while, it could get really interesting, but I'm going to cut it off right now. Okay, so you want to get the idea behind all this, okay? The idea behind the whole way we actually use mathematics in the real world, which is probably the most relevant thing that you can take out of this course. Of course, you also have to take out the techniques and the operations and all the stuff that you need in order to do this, or at least to understand well what's going on, okay? So we got this data and we got this graph, okay? It's explained on the MCR. I'm not going to explain it again. It's real easy to go from data to graph. Check out the videos. Just briefly, we counted a 51 centimeter pendulum for 15 seconds, a 42.5 centimeter pendulum for 10 seconds. Why did we use different times? That would assure that some of it is kind of screwed up, and data usually is, so we didn't want perfect data. Okay?
Wouldn't want that.
And then we wanted to think a little bit about how the short time period might screw things up, and then we observed that it did. But you can check the videos on that. The basic idea is we get this data, and then we can easily calculate frequencies. For example, if we counted 20 in 15 seconds, how many would we count in a minute? Now, y'all are too slow in this. You haven't done enough time. You haven't spent enough time watching the second hand on a clock in class.
We don't have an analog clock.
I know, you don't have second hands. The clocks don't measure seconds. It's ridiculous. How do people learn any mathematics? Because that's the main source of mathematical knowledge, is watching the clock, hoping class will be over soon, but then watching the clock makes it drag out, right?
We just really love this class so much that we don't watch the clock.
Yeah, we pay so much
Well,
attention.
yeah, then you could dread the clock, okay? One way or another, you have an emotional reaction to that clock that's missing, since everybody has stupid digital clocks.
Yeah.
Okay,
Hence
including
what you
us,
got.
except I've got a real one there, but the second hand doesn't work. It's irritating.
Well,
Okay.
So we're back to square one. It's so funny.
So obviously-
It doesn't work.
Obviously, I don't really want you to learn much because I don't have that clock. Now, I should carry that clock around, one on my forehead and one on the back of my head. But then you don't really want to look at me, you want to look at the clock. Okay, I get it. Now,
Okay, repeat the question again.
digression aside, if you don't see immediately that you would count 4 times this many in a minute,
Yes.
then you aren't familiar with second hands. That's all there is to it. 15 minutes is a quarter of a minute, right? 15 seconds is a quarter of a minute. And you watch hour hands, you know, some clocks have those but don't have second hands. And you know 15 is a quarter of 60 because you look at clocks. Okay? Because there are clocks that aren't digital clocks. Hopefully you look at them once in a while. Okay, well, one way or another, you should immediately see that that corresponds to 80 counts per minute. Now, as I said, we're counting half cycles. To get the cycles, you would have half as many cycles as you have half cycles. Something is happening to my camera. It wasn't an earthquake, but
It
I
was
think I
just
need
heat.
to move this thing before motion of this chair won't affect it.
Gosh, Candace.
I won't say who the culprit is.
But we all know it's Candace.
what? I don't understand what's happening right now.
Yeah, don't name names, you know, this has gone out on the internet, of course, nobody knows which Candace we have.
Candace is the one he pets like a dog.
I'm sorry? Hey, you keep bringing it up, I don't know. Are you ready? Okay, we're wasting too much time with digression, so let me get focused here. Anyhow, so for length of 51 centimeters, we get 40 cycles per minute, and that's how it's calculated. It's very simple. So we do those calculations, and we get a graph that looks like this. And then we determine that these points kind of look like they might lie in a straight line, but if you connect this to this, all the points lie below the straight line, telling you that there appears to be some curvature. You've got a pretty significant bit of evidence that there's a little curvature to this thing. Okay? Now I'll tell you what physics predicts, but I'm not going to tell you just yet. Okay, so, and I won't go through all the physics of it. It involves differential equations and stuff, you don't know. Okay, so we have this graph. Now, we digressed for a bit because we set these points here, and this just depicts the points, and it depicts the slopes between our data points. Okay? Now, if you ran MCR, don't answer. Clearly, the slopes should all be negative because it's always gone downhill, right? So if you had a slope that came out positive from these data points, what would that tell you?
We're wrong.
Huh?
We're wrong.
It tells you there's something wrong with the data. Now, that might be that because this is the data point involved, you only counted for 5 seconds, right? Mm-hmm. So there's a lot of uncertainty in the data because it's a short time period and you have a small count. Maybe it was really 9.49, but you know the 5-second limit happened just before your next count, right? That would significantly affect the 54 is it that we have here, right? Mm-hmm. Okay. So that might really only be 50, or it might be 58 or something. Okay. So we would have a significant effect on any data point that joins up with this one, here or here. So there's some evidence already that we have some uncertainties in our data. Now this comes out of the idea of a scatter graph. This is a scatter graph. We just plot all our data points, that's a scatter graph. So if somebody wanted to know what the scatter graph was, right? So we did this exercise. I was going to do this exercise anyhow, but I did it in answer to the question of what's a scatter graph. Okay?